Good morning, everybody, and happy December 12th. Christmas is a mere 13 days away. That's less than 2 weeks from now. Still have lots of calculus to do, though, and let's get started looking for compartment number 12 on our Advent calendar before we get into today's calculus problem. Let's see. There's 13, there's 11, 12. It's right down here. Okay, let me zoom in for you. Number 12. It's right next to this fruit. Looks like that's probably an apple. There's a little birdie. Do you think there's a bear behind here? I sure hope so, but I don't think so. I mean, there's no bear in the proximity. You know, there's this bear over here, but I don't know. I'm going to get into this compartment, get the chocolate, and I'll put today's calculus question on screen for you to enjoy looking at while I do this. We're actually doing something from the BC exam today. Polar curves, doing some area calculus. Oh, yes! Yes! Whoa! Let's go! Bear! Yes! Wow! All right. Good. Okay. Look at that. Check it out. We finally got one of these bears. Okie dokie. Oh man, okay, I gotta calm down to do this calculus. It's like midnight here. It's so early. It's cold. It's December. It's winter. It's a bear. It's a chocolate bear. Oh yeah. Look at that. I love bears. You know, I live on Cape Cod. We don't even have bears here. But this isn't where I grew up. You know, I grew up in Bear City, Bear Central. I'd get texts when I went to college, you know, it'd be like, warning, there's a bear just running around campus. Just be careful. All right, I'm going to eat this bear, and you can continue reading the problem here. We've won the day, folks. We have won the day. Just when I thought we weren't going to get a bear, we got one. All right, let's do the calculus. This is problem 4 from the 2009 AP Calc BC Form B exam. So this was part of the no calculator section, and this is on polar curves, something which is not in the AB exam. The graph of the polar curve r equals 1 minus 2 cosine theta for theta between 0 and pi is shown above. We see this beautiful curve here. Let S be the shaded region in the third quadrant bounded by the curve and the axis, so we can see the region S there. Part A is to write an integral expression for the area of this shaded region S. So we just have to write the expression, we don't have to evaluate it. This is a pretty straightforward question, you just gotta remember how to find the area of a polar region. It of course is going to be an integral, and we have a 1/2 out front, and then the radius, or r, squared. In this case, r is given to us as 1 minus 2 cosine theta, and we need to square this, and the integral is taken with respect to theta. Remember, this 1/2 and the radius squared comes from the fact that when we figured out how to do this originally, it comes from the area of a sector of a circle. Just like traditional integrals are built from rectangles, polar integrals are built from sectors of circles, and that's why we have 1/2 integral r squared. That's how we're going to calculate the area of this region. The question is, what are the bounds, the lower bound and the upper bound? Well, we have to think. Let's look at this picture. We see that the region S starts where r equals -1. So we need to figure out what theta value gives us an r of -1. That will be the lower bound of our integral. Now the curve, or the region I should say, is closed. The region is closed when the curve comes back to this point, the origin. That's where r equals 0. So we'll also have to figure out where does theta make r equal to 0, and that's going to be the upper bound of the integral. Let's begin with -1. So we'll write 1 minus 2 cosine theta, that's our r, is equal to -1. Subtract 1 from both sides, and we find that -2 cosine theta equals -2. Divide both sides by -2, and we find that cosine theta equals +1, and thus theta equals 0. Cosine of 0 is 1, so theta is 0. That's the lower bound of our integral, and we'll do a similar thing for r equals 0. We'll say that 1 minus 2 cosine theta equals 0. Remember, we're trying to find the upper bound of our integral now. And let's add 2 cosine theta to both sides. So 1 equals 2 cosine theta. And then divide both sides by 2, so 1/2 equals cosine theta. And if you remember your unit circle, which you should, this means theta has to equal pi over 3. Cosine takes on a value of 1/2 at the angle pi over 3. So that's the upper bound of our integral, and that actually completes the answer to part A. That is our integral expression. Remember, this all comes from the standard way that we calculate the areas of polar regions, which is integrating from a to b, 1/2 out front, r squared d theta. This is how you find the area of a polar region, and that's all we did for part A. All right, moving on to part B. Write expressions for dx d theta and dy d theta in terms of theta. Okay, so you'll have to remember some formulas for this. We know that x is equal to r cosine theta, and y is equal to r sine theta. These are relationships between Cartesian coordinates and polar coordinates that you should know. Now, in order to find dx d theta, we're going to have to take the derivative of this equation, which is going to involve a dr d theta, because we're going to have to take the derivative of r. So let's just go ahead and find that first. Let's find dr d theta. We know that r is 1 minus 2 cosine theta. And if we take the derivative of that, we're just going to get 2 sine theta. So that's what dr d theta is. All right, now we can go ahead and take the derivative of x and the derivative of y. Let's start with x. Taking the derivative of this equation, both sides, we're taking the derivative with respect to theta. On the left, we have dx d theta. On the right, we have to use the product rule because we have a product of functions, r, which changes with respect to theta, and cosine theta, which of course is also changing. So the product rule is f prime g plus g prime f. In this context, that's dr d theta cosine theta plus the derivative of cosine theta, which is negative sine. So let's just write minus sine theta times r. Dr d theta, of course, we know, is 2 sine theta. So this is just 2 sine theta cosine theta. And then we are subtracting sine theta times r, but of course r is just 1 minus 2 cosine theta. So we have minus sine theta times r, which is 1 minus 2 cosine theta. Now notice on the left we have 2 sine theta cosine theta. If we were to distribute over here on the right, we'd have minus sine theta times minus 2 cosine theta. So that would be another 2 sine theta cosine theta. In total then, we have 4 sine theta cosine theta. The other term we would have is minus sine theta times 1, which is just minus sine theta. And that is dx d theta. Next, we'll do a similar procedure in order to find dy d theta. So we're going to take the derivative on the left and right side of this equation with respect to theta. I'll write that here, dy d theta. What is this going to be? Well, again, it's the product rule. F prime g, so dr d theta, times sine theta, plus g prime f, so cosine theta times r. Dr d theta, of course, we know is 2 sine theta. So dr d theta times sine theta is 2 sine theta times sine theta, so 2 sine squared theta. Then we add cosine theta r, But of course, we know that r is 1 minus 2 cosine theta. So that is our expression for dy d theta, and thus we have completed part B, which was just to write expressions for dx d theta and dy d theta in terms of theta. So we didn't want any r's in there, and indeed, these are those final answers. Moving on to part C. Part C asks us to write an equation in terms of x and y for the line tangent to the graph of the polar curve, this one here, of course, at the point where theta equals pi over 2. And we want to show the computations that lead to our answer. Now, to write the equation of a tangent line, we're going to need a point and a slope. A point is a pair of x and y coordinates. We know that x equals r cosine theta, and we know that y equals r sine theta. So, since we're looking for the tangent line at theta equals pi over 2, we can figure out what the x and y coordinates have to be. When theta equals pi over 2, x is r times cosine of pi over 2. Cosine of pi over 2, though, is 0. So x would be r times 0, which is just 0. As for y is r times sine of pi over 2. Sine of pi over 2 is 1, so y would just equal r. But we know r is 1 minus 2 cosine theta, but theta is pi over 2, so it's 1 minus 2 cosine pi over 2. Cosine pi over 2 is 0, so y is just 1. Thus, the point on the curve that our tangent line is passing through at pi over 2 is the point 0, 1. So we can start to write the equation of the tangent line now. Y minus 1, that y coordinate, equals the slope, which we'll figure out, multiplied by x minus the x coordinate, 0. Now, I shrunk our work in part B to make a little bit more room. To find the slope, we need to look at dy dx, because we are trying to write this equation in terms of y and x. So what is dy dx? Well, to find it, we need to take dy d theta and divide it by dx d theta. And let's just write this whole time, what we're actually doing is evaluating this, dy dx, when theta equals pi over 2. So I'll put this vertical line that means we're evaluating the expression at theta equals pi over 2. To evaluate this, let's first focus on the numerator, dy d theta, when theta is pi over 2. Looking at our previous work, this is dy d theta. So what is it when theta is pi over 2? Well, cosine of pi over 2 is just 0, so this term would disappear. Sine of pi over 2 is 1, so sine squared pi over 2 is 1, and so 2 sine squared pi over 2 is 2. Okay, so the numerator then is 2. That's dy d theta evaluated at theta equals pi over 2. As for the denominator, dx d theta, when theta is pi over 2, let's look at our previous work right here. Again, cosine of pi over 2 is 0, so this term disappears, and all that's left is negative sine of pi over 2. Sine of pi over 2 is 1, so that would be negative 1, and thus the slope is negative 2, and we can plug that into this box. I'll just erase the box. We know what the slope is now. It's negative 2, and that is our tangent line. Or if you prefer to put it in slope-intercept form, you could say this is just negative 2x because the 0 doesn't matter, and then add 1 to both sides, and you'd find that y equals negative 2x plus 1. And that completes our solution to part C. And that's how you solve free response question 4 from the 2009 AP Calc BC exam. Let me know in the comments if you have any questions, and be sure to check the description for the link to the full AP Calculus free response question advent calendar so you don't miss another episode and can catch up on any you've missed. There'll also be a link to my Calculus 1 exercises playlist so you can get even more practice. Thanks for watching, and I'll see you tomorrow for the next episode of our advent calendar.